Lieutenant Viktor Belenko levels the MiG-25 Foxbat at 500 feet over the Sea of Japan. Fuel gauge touching zero. The coast of Hakodate 8 minutes ahead if the Tumansky turbojets don't flame out first. The world's fastest interceptor was never designed to fly this low, this far, this heavy in sea-level air. And the fuel consumption rate has spiked 40% above his pre-flight calculations. Behind him, 2 MiG-23 interceptors are climbing out of Dolinsk Sokol with orders to shoot him down before he crosses into Japanese airspace. Belenko has shut off his IFF transponder and radio, so Soviet ground control cannot jam his flight surfaces or detonate the aircraft remotely. But that also means he is navigating by dead reckoning and horizon reference alone. No navigation aids, no ground guidance, no divert options if the fuel runs out. The decision was binary: defect with the aircraft Western intelligence had been hunting for a decade, or spend the rest of his life flying intercept profiles against American reconnaissance planes he would never catch. The turbojets are still running. The coastline is not yet visible. Earlier that month, September 1976, Belenko had been flying intercept profiles from Chuguyevka Air Base in Primorsky Krai, practicing runs against simulated SR-71 Blackbird tracks at 80,000 feet. The mission was always the same: light off the R-15B 300 engines, climb at maximum thrust until the altimeter read 24,000 meters, acquire the target with the RP-25 Smerch-A radar, fire 2 R-40 missiles, then descend before the engines consume themselves. Soviet engineers had designed the MiG-25 as a high-altitude interceptor, not a fighter, and every component reflected that single purpose. The airframe was welded nickel steel, chosen because it could withstand kinetic heating at Mach 2.8 without the expense or machining difficulty of titanium. The engines were brute-force turbojets that gulped fuel at 15,000 kilograms per hour at full throttle, and their time limit at maximum speed was 5 minutes before turbine blades began to warp and crack. Belenko had flown 73 intercept sorties in 18 months, and he knew the performance envelope down to the kilogram and the second. The training was repetitive, the targets were hypothetical, and the aircraft was never allowed to fly low enough or far enough to reach a foreign border. The RP-25 Smerch-A radar mounted in the MiG-25's nose generated 600 kilowatts of peak power during each transmission pulse, a figure that dwarfed every other fighter radar in service. The system used 18 vacuum tubes in the transmitter section, each tube the size of a soup can, bolted into a steel chassis with hand-soldered connections and manual tuning adjustments. Detection range against a bomber-sized target was 100 kilometers, and the radar could track while the aircraft maneuvered at 9 times the force of gravity, enough to gray out the pilot's vision. Soviet engineers had chosen vacuum tube technology, not because they lacked the ability to build solid-state components, but because tubes could be manufactured in quantity, replaced in the field, and operated at power levels that would instantly destroy transistorized circuits. The radar weighed 350 kilograms, far heavier than Western equivalents, but weight was not a constraint in an interceptor that never dogfought and rarely descended below 60,000 feet. What mattered was power, range, and reliability under conditions that would shatter more delicate electronics. And the RP-25 delivered all three. Western electronic intelligence stations had been intercepting MiG-25 radar emissions since 1971, when the first operational squadrons deployed along the Soviet border with China. Analysts at the National Security Agency cataloged the signal characteristics: S-band frequency, high pulse repetition rate, transmission power far above the standard for Soviet radars. The equipment was easy to identify because vacuum tube oscillators generated a distinctive harmonic signature, a fingerprint that solid-state transmitters could not replicate. Intelligence reports filed between 1972 and 1975 consistently described the radar as obsolete, built with decade-old components, evidence of Soviet technological backwardness. One assessment noted that the United States had phased out vacuum tubes in airborne radar by 1965, and the persistence of tube technology in a frontline interceptor suggested that Soviet engineers lacked the manufacturing base or expertise to produce modern solid-state systems. The conclusion was filed, circulated, and accepted. The MiG-25 was fast, but its electronics were primitive. No one asked why the Soviets would pair a Mach 3 airframe with a radar they knew was inferior. Soviet ground crews at forward air bases could swap a burned-out vacuum tube in the RP-25 radar in 15 minutes using nothing more than a socket wrench, a multimeter, and a replacement tube pulled from a wooden crate. The procedure required no clean rooms, no calibration rigs, no depot-level technicians. A crew chief would open the radar bay access panel, identify the failed tube by checking its filament glow, unbolt the socket clamp, pull the tube from its mount, insert the replacement, tighten the clamp, and power up the system to verify transmission. If the radar generated a pulse and the indicator lamp lit green, the aircraft was mission ready. Tubes failed regularly because they operated at extreme power levels and temperatures, but failures were predictable and the replacement process was trivial. In Arctic conditions at -40 degrees Celsius, crews worked inside heated tents with portable generators, and they kept the aircraft operational at readiness rates that Western analysts refused to believe until Belenko confirmed them after his defection. The simplicity was intentional, designed for a conscript maintenance force with minimal training and an air force that prioritized availability over performance refinement. On September 6, 1976, at 13:11 local time, Belenko advanced the throttles on his MiG-25 and lifted off from Chuguievka Air Base on what the tower log recorded as a routine training sortie. He climbed to 6,000 meters, leveled off, and then turned east toward the Sea of Japan instead of north toward the designated intercept training area. Soviet ground control noticed the deviation within 3 minutes and radioed instructions to return to the assigned flight path. But Belenko had already switched off his radio and IFF transponder, severing the electronic link that allowed controllers to monitor his position and, if necessary, transmit override commands to the aircraft. The decision had been made weeks earlier, but the execution window was narrow. He needed clear weather over the Sea of Japan, enough fuel to reach Japan, and a training sortie that would give him altitude and distance before ground control realized the deviation was deliberate. He had calculated the fuel load to the kilogram, planned the routing to avoid known radar sites, and rehearsed the cockpit procedures for flying without navigation aids, because once the transponder went dark, he would be navigating by compass heading and visual reference to the horizon. Belenko had loaded 14,570 kilograms of fuel before takeoff, enough for 400 miles at low altitude, with zero reserve and no divert options if weather or mechanical failure forced him off course. The MiG-25's fuel consumption rate was brutal at sea level because the engines were optimized for thin air at high altitude, and flying at 500 feet would burn fuel at nearly twice the rate of a cruise at 60,000 feet. He had calculated the distance from Chuguievka to Hakodate Airport at 370 miles, leaving a margin of roughly 30 miles or 4 minutes of flight time. And that margin assumed he could navigate a straight-line course with no evasive maneuvering. Soviet interceptors would be scrambling within minutes, and if they forced him to turn or climb, the additional fuel burn would drain the tanks before he reached the coast. The gauges were mechanical, not digital, and they were notoriously unreliable in the final 10% of tank capacity, so he would not know if he had miscalculated until the low-pressure warning lights illuminated and the engines began to starve. There was no contingency plan, because landing short meant ditching in the Sea of Japan, and the MiG-25 would sink in less than a minute. With the radio and IFF transponder shut off, Belenko lost all ground control guidance and had to rely on dead reckoning and horizon reference to maintain his heading toward Japan. The MiG-25's inertial navigation system was functional, but it required manual updates from ground stations to correct for drift, and without those updates, the system would accumulate errors at a rate of several miles per hour. He used the magnetic compass and the angle of the sun to verify his eastward heading, cross-checking against the coastline features he could see to his left as he paralleled the Soviet shore. The aircraft had no terrain-following radar, so flying at 500 feet over water required constant visual reference to the horizon and manual adjustment of the control stick to prevent descent into the waves. Cloud cover would have been catastrophic, because climbing above the clouds would expose him to Soviet coastal radar, and descending into them would eliminate the horizon reference he needed to stay level. The sea surface was calm, the visibility was good, and he held the throttles at 90% to balance speed against fuel consumption, knowing that every minute at this altitude brought him closer to the point where the engines would quit, regardless of how carefully he flew. At 13:28 local time, Soviet Air Defense Command detected Belenko's deviation from the assigned flight path and scrambled two MiG-23 Flogger interceptors from Dolinsk-Sokol Air Base on Sakhalin Island, with orders to intercept and, if Belenko refused to return, to shoot him down before he crossed into Japanese airspace. The MiG-23s had a higher top speed at low altitude than the MiG-25, and they were already airborne and vectoring toward his last known position when Belenko began his descent to 500 feet. By flying that low, he dropped below the effective coverage of Soviet coastal radar, which was optimized to detect high-altitude bombers, and could not reliably track a target skimming the wave tops. The MiG-23 pilots would have to find him visually, and in the late afternoon light over a featureless ocean, that would be difficult unless they knew exactly where to look. Soviet doctrine called for defecting pilots to be engaged without warning, because the priority was to destroy the aircraft and prevent its capture, not to recover the pilot. Belenko knew this, which was why he had committed to the low-altitude run the moment he turned off the transponder. There would be no radio calls, no second chances, only the race to cross 200 miles of open water before the interceptors found him or the fuel ran out. At 500 feet above the Sea of Japan, the air was dense, and the engines were gulping fuel at a rate 40% higher than Belenko had calculated for a high-altitude cruise. The R-15B 300 turbojets were designed to operate most efficiently in the thin air above 60,000 feet, where lower drag and higher true airspeed compensated for the engine's poor low-altitude performance. At sea level, the engines had to work harder to produce the same thrust, and the increased fuel flow meant that his 30-mile margin was evaporating with every passing minute. He could see the fuel gauges dropping, but the mechanical indicators were too coarse to give him an accurate reading of how much time he had left, so he relied on elapsed time and mental arithmetic to estimate when the tanks would run dry. Climbing back to altitude would improve fuel economy, but it would also put him back on Soviet radar and give the MiG-23s a clear shot. The decision was already made. Stay low, accept the fuel penalty, and hope that the turbojets kept running long enough to reach the coast. He checked the chronometer on the instrument panel. 8 minutes to the coastline, if the winds held and the engines did not quit. At 13:58 local time, Viktor Belenko touched down on the civilian runway at Hakodate Airport, with the fuel gauges reading approximately 120 kilograms, which translated to roughly 2 minutes of flight time remaining before the turbojets would flame out and the aircraft would become a 20-ton glider. The landing was not gentle, because he had no time to set up a proper approach pattern, so he descended straight in from the east, dropped the landing gear, and put the main wheels on the pavement at 180 knots, well above the recommended touchdown speed. The brakes overheated immediately, but the runway was long enough to allow the aircraft to decelerate without thrust reversers, and he rolled to a stop near the midfield taxiway, shut down both engines, and opened the canopy. Japanese civilians and airport personnel ran toward the aircraft, confused by the sudden arrival of a Soviet military jet, while Belenko climbed out of the cockpit and surrendered to the first security officer who arrived. The MiG-25 sat on the runway, engines ticking as they cooled, the fuselage still radiating heat from the low-altitude sprint across the Sea of Japan. And within an hour, the Japanese self-defense forces had cordoned off the entire airport and notified the U.S. Embassy in Tokyo. Japanese and American diplomats negotiated the transfer of the MiG-25 over the next 19 days, while Soviet officials demanded the immediate return of both the pilot and the aircraft under international law. The United States invoked the principle of political asylum for Belenko and offered to return the aircraft after a brief inspection, a proposal the Soviets rejected because they knew that any inspection would compromise the MiG-25's most sensitive systems. On September 25th, U.S. Air Force technicians disassembled the MiG-25 into components small enough to fit inside a C-5 Galaxy transport, loaded the fuselage, wings, engines, and avionics into the cargo bay, and flew the entire package to Wright-Patterson Air Force Base in Ohio. The Foreign Technology Division at Wright-Patterson had 60 days to inspect, measure, photograph, and test every component before diplomatic pressure would force the U.S. to return the remains to the Soviet Union. Engineers cleared a hangar, assembled a team of radar specialists, metallurgists, propulsion analysts, and avionics technicians, and began the disassembly process the day the aircraft arrived. The MiG-25 represented the first intact example of a Soviet interceptor designed to hunt American strategic bombers and reconnaissance aircraft, and no one knew whether the technology inside would validate or overturn a decade of intelligence assessments. Engineers at Wright-Patterson's Foreign Technology Division removed the RP-25 radar assembly from the MiG-25's nose and laid it out on the inspection bench. And the first reaction was laughter. The transmitter section contained 18 vacuum tubes, each one the size of a soup can, mounted in a steel chassis with hand-soldered connections and tuning adjustments that had to be made manually with a screwdriver. The wiring harness used cloth-insulated copper wire, a technology the United States had phased out in the 1950s, and the chassis itself was stamped steel with riveted seams, not the lightweight cast aluminum used in American radars. One engineer remarked that the assembly looked like something from a World War II bomber, and the consensus in the room was that Soviet electronics had lagged Western technology by at least 15 years. The radar weighed 350 kilograms, more than twice the weight of the AN/APG-63 radar in the F-15 Eagle, and the size of the components suggested that Soviet engineers either lacked access to miniaturized solid-state parts or did not understand how to use them. The laughter persisted until the lead engineer connected the radar to a bench power supply and activated the transmitter to measure the output. The lead engineer powered up the RP-25 radar and triggered a transmission pulse, and the peak power meter registered 600 kilowatts, a figure so far above the expected range that he assumed the meter was malfunctioning. He recalibrated the instrument, ran the test again, and got the same result: 600 kilowatts peak output during the pulse, sustained for a fraction of a second before the transmitter cycled down. For comparison, the AN/APG-63 radar in the F-15 generated 10 kilowatts of peak power, and the most powerful ground-based search radars in the U.S. inventory operated at around 100 kilowatts. The Soviet radar was transmitting 6 times as much power as the largest American ground system, and 60 times as much as a contemporary fighter radar. The engineer ran a burn-through test, simulating the effect of a jamming signal at various power levels and distances, and found that the MiG-25's radar could maintain target lock through jamming that would completely blind an American radar. The room went quiet. No one was laughing anymore, because the implications were immediate. Every jamming pod, every electronic warfare system, every tactical doctrine built around the assumption of Soviet radar inferiority was now suspect. The vacuum tubes were not a sign of backwardness. They were a brute force solution to a problem American engineers had not even considered. Engineers designed a test to measure the RP-25 radar's resistance to electromagnetic pulse, or EMP, the burst of high-voltage radiation generated by a nuclear detonation that can destroy unprotected electronics. They placed the radar assembly in a shielded test chamber and exposed it to a simulated EMP pulse with a field strength of 50 kilovolts per meter, a level consistent with the environment inside a nuclear battlefield. The vacuum tubes continued to operate without interruption. The radar maintained lock on a simulated target, and post-test inspection showed no damage to any component. For comparison, they ran the same test on a solid-state reference unit, a radar module taken from an F-4 Phantom, and the EMP pulse shorted every transistor junction in the circuit within microseconds, rendering the unit permanently inoperative. The result was unambiguous. Vacuum tubes could survive an EMP pulse that would instantly kill a solid-state system, and the MiG-25 had been designed from the beginning to operate in a nuclear environment, where American fighters would be grounded because their electronics were fried. According to the test report filed by the Foreign Technology Division, the Soviet decision to use vacuum tubes was not a technological compromise, but a deliberate choice driven by the expectation that any air war between NATO and the Warsaw Pact would involve tactical nuclear weapons. The reason vacuum tubes survived EMP pulses while solid-state components did not was a matter of basic physics. A vacuum tube operates by thermionic emission. A heated cathode boils off electrons, which flow across a vacuum gap to an anode, and the flow can be controlled by a grid wire between them. The vacuum gap contains no semiconductor material, so there is nothing for ionizing radiation to disrupt. In contrast, a transistor relies on carefully controlled layers of doped silicon, and a high-energy electromagnetic pulse injects stray electrons into the semiconductor lattice, creating short circuits that destroy the junction permanently. Vacuum tubes were heavier, bulkier, and consumed more power than transistors, but they were immune to radiation effects that would cripple a solid-state circuit. Soviet engineers had chosen tubes not because they could not build transistors, but because tubes could be operated, repaired, and replaced in an environment where EMP pulses from nuclear airbursts would be a routine feature of air combat. The engineering trade-off was clear. Accept the weight penalty and power consumption in exchange for survivability in a nuclear war, and the MiG-25's designers had made that choice deliberately and consistently across every electronic system in the aircraft. Engineers calculated the jamming-to-signal ratio for the MiG-25's radar in a typical intercept scenario, comparing the RP-25's 600 kilowatt transmission against a standard US jamming pod output of 10 kilowatts. At a range of 50 kilometers, the radar signal arriving at the jammer was strong enough that the jammer's 10 kilowatt output could not mask it, and the radar maintained a clear track on the target. The ratio was 60-1 in favor of the radar, meaning the MiG-25 could burn through jamming that would completely blind a radar operating at normal power levels. Western electronic warfare doctrine assumed that jamming pods could degrade or break radar lock by flooding the receiver with noise, but that assumption was based on Soviet radars operating at 5 to 10 kilowatts, not 600. The RP-25's brute force approach rendered jamming pods ineffective unless the jamming aircraft could generate power levels that were physically impossible with airborne equipment. Soviet engineers had not tried to build a precise, efficient radar. They had built a radar that transmitted so much power that no jammer could compete, and the vacuum tubes made that power level achievable because they could handle voltages and currents that would instantly destroy a transistor. The result was a radar that could not be countered by any electronic warfare system in the U.S. inventory. During debriefing sessions at a classified location in the United States, Viktor Belenko confirmed that Soviet MiG-25 squadrons maintained aircraft availability rates above 85%, a figure Western intelligence analysts had dismissed as propaganda when they first intercepted it from Soviet communications. Belenko explained the maintenance procedure in detail. Ground crews kept wooden crates of spare vacuum tubes at every forward airbase, and when a tube failed, a technician would open the radar bay, identify the bad tube by checking the filament, unbolt it, insert a new one, and verify operation with a portable test set. The entire process took 15 minutes and required no specialized tools, no clean rooms, and no depot-level repair facilities. In contrast, American solid-state radar modules required precise calibration, controlled environments, and replacement procedures that took hours, and failures often meant that the aircraft had to be grounded until a replacement module could be flown in from a central depot. The Soviet approach accepted frequent failures, because failures were trivial to fix, while the American approach minimized failures, but made each failure a logistical crisis. Belenko's testimony validated the engineering philosophy behind the vacuum tube decision, and it forced U.S. planners to reconsider assumptions about Soviet operational capability that had guided procurement and doctrine for a decade. The contrast between Soviet and American maintenance practices became starkest when engineers compared the MiG-25's vacuum tube radar to the AN/APG-63 radar in the F-15 Eagle, which used solid-state modules that required clean room calibration and a 12-hour replacement cycle when a module failed. The F-15's radar was lighter, more precise, and more power efficient than the RP-25, but it was also far more fragile and far more difficult to repair. A failed module had to be removed, shipped to a depot, tested, replaced with a spare from inventory, and the new module had to be calibrated using specialized test equipment that was not available at forward airbases. If a spare was not immediately available, the aircraft could be grounded for days or weeks, and the complexity of the solid-state system meant that only highly trained technicians could perform the repair. The F-15 was a superior fighter in almost every performance metric, but its radar was vulnerable to EMP and difficult to maintain, while the MiG-25's radar was immune to EMP and could be fixed by a conscript technician with a socket wrench. The engineering philosophies were diametrically opposed. American systems optimized for performance and efficiency. Soviet systems optimized for survivability and maintainability, and neither approach was universally superior because the answer depended on the scenario. In 1978, Soviet MiG-25RB reconnaissance variants deployed to Egyptian air bases and began flying intercept profiles against U.S. 6th Fleet aircraft operating over the Mediterranean. And the encounters revealed the full operational impact of the RP-25 radar's burn-through capability. The MiG-25RB carried the same RP-25 radar as the interceptor variant, and Soviet pilots used it to track U.S. Navy aircraft at ranges and under conditions where American crews expected their electronic warfare systems to provide protection. The deployments were not publicized, but U.S. Navy electronic warfare officers began reporting intercepts where Soviet radars maintained lock despite active jamming. And the reports were consistent enough that the Office of Naval Intelligence initiated a formal investigation. The key question was whether Soviet radar technology had improved or whether U.S. jamming doctrine was based on incorrect assumptions about Soviet power levels. And the answer, derived from the Wright-Patterson teardown and confirmed by operational encounters, was that the Soviets had been operating 600-kilowatt radars for years, while U.S. jamming pods were calibrated to counter radars in the 5 to 10 kilowatt range. The mismatch was not a sudden development. It had existed since the MiG-25 entered service in 1970. But Western intelligence had not recognized it because analysts dismissed vacuum tube technology as obsolete. A U.S. Navy EA-6B Prowler flying an electronic warfare mission off the coast of Egypt detected a MiG-25RB intercept on its radar warning receiver and activated the ALQ-99 jamming pod in response. The ALQ-99 was the most advanced airborne jamming system in the U.S. inventory, capable of generating 5 kilowatts of jamming power across multiple radar frequency bands simultaneously, and it had been designed to degrade or break the lock of Soviet S-band radars used in surface-to-air missile systems and fighter aircraft. The electronic warfare officer in the Prowler's rear seat monitored the RWR display and confirmed that the jamming pod was transmitting at full power, flooding the radar frequency with noise that should have masked the Prowler's return signal and forced the Soviet radar to lose track. Standard doctrine called for the jamming to be maintained while the Prowler executed a hard turn and dispensed chaff to create false targets, and the EWO followed the procedure exactly. The jamming pod was working, the chaff was in the aircraft was maneuvering, and the RWR display continued to show the Soviet radar locked on, tracking through every countermeasure as if the jamming were not there at all. The MiG-25's RP-25 radar transmitted a 600 kilowatt pulse that burned through the Prowler's 5 kilowatt jamming signal at a range of 60 kilometers, maintaining a continuous track on the target despite the jamming pod operating at full power. The physics were straightforward. The radar's signal was strong enough at the receiver that the jamming noise could not mask it, and the jamming-to-signal ratio was so low that the radar's tracking algorithms filtered out the noise and locked on to the Prowler's actual return. The Prowler's electronic warfare officer watched the RWR display and saw the Soviet radar signal strength increasing as the MiG-25 closed the range, and there was no indication that the jamming was having any effect. He activated additional jamming modes, varied the frequency, and increased the power output to the maximum the system could sustain. But the RWR continued to display a solid lock. The chaff cloud, which should have created multiple false targets and forced the radar to break lock while it sorted through the returns, was ignored entirely. Because the RP-25's high power allowed it to distinguish the Prowler's metal airframe from the lightweight chaff strips. The crew had no countermeasure that worked, and the MiG-25 continued to close, the radar tracking perfectly until it reached R-40 missile range. The MiG-25 closed to 35 kilometers, well within the launch envelope of the R-40 air-to-air missile. And the Prowler crew heard the radar warning receiver shift to a higher-pitched tone, indicating missile acquisition mode. Soviet doctrine called for the MiG-25 to fire 2 R-40s in rapid succession, one radar-guided and one infrared-guided, to defeat countermeasures. But this intercept was a peacetime encounter, so the MiG pilot simulated the launch, held the lock for 5 seconds to confirm that the fire control system had a valid solution, and then broke off, climbing back to altitude and turning east toward Egyptian airspace. The Prowler crew watched the radar return fade from the scope, and the RWR display went silent. The aircraft was undamaged, the crew was safe, but the encounter had demonstrated that the standard electronic warfare playbook was useless against a Soviet radar that could burn through jamming by sheer power. The Prowler landed at its carrier, and the electronic warfare officer filed a detailed mission report describing the intercept, the jamming pod's failure to break lock, and the lack of any effective countermeasure. The report was classified secret and forwarded to the Office of Naval Intelligence, where analysts compared it to similar reports from other Sixth Fleet aircraft and concluded that the MiG-25's radar represented a fundamental challenge to U.S. electronic warfare doctrine. The Prowler crew's debrief session took place in a secure compartment aboard the aircraft carrier, and the initial assumption among the maintenance officers was that the ALQ-99 jamming pod had malfunctioned during the intercept. Technicians pulled the pod, ran diagnostics, and found that every component was operating within specifications. The transmitter was generating 5 kilowatts across the correct frequency bands, the antennas were radiating properly, and the control system had executed the correct jamming modes in response to the radar threat. The equipment had not failed, it had been overpowered. The intelligence officer present at the debrief pulled the classified assessment from the Foreign Technology Division's teardown of Belenko's MiG-25 and read the key finding aloud. The RP-25 radar generates 600 kilowatts of peak power, 60 times higher than the jamming pod's output. And at that power level, the radar can maintain lock through jamming at ranges up to 60 kilometers. The numbers explain the encounter perfectly. The Prowler's jamming pod was designed to counter Soviet radars operating at 10 kilowatts or less, and the MiG-25's radar was 600 times more powerful than that baseline. The doctrine was based on incorrect assumptions, and every U.S. aircraft in the Sixth Fleet was vulnerable to a threat that could not be jammed. In 1980, the U.S. Air Force initiated a suppression of enemy air defenses upgrade program to address the jamming power deficit revealed by the MiG-25 encounters, and the first modification was to increase the output of the ALQ-131 jamming pod from 10 kilowatts to 15 kilowatts. The upgrade required a redesigned transmitter, a heavier power supply, and additional cooling to dissipate the heat generated by the higher power output. And the modifications added 12 kilograms to the pod's weight and increased its cost by 20%. Even with the upgrade, the jamming-to-signal ratio against a 600 kilowatt Soviet radar was still only 40-1 in favor of the radar, which meant that jamming could degrade but not break the lock. Engineers calculated that matching the MiG-25's power level would require a jamming pod generating 600 kilowatts, which was physically impossible for an airborne system because the weight, power draw, and thermal management requirements would exceed the carrying capacity of any tactical aircraft. The conclusion was stark. U.S. aircraft could not outjam a Soviet radar operating at that power level. So the doctrine had to shift from jamming to evasion, and pilots would have to rely on speed, altitude, and terrain masking to avoid intercepts that their electronic warfare systems could not counter. EMP hardening became mandatory for all U.S. tactical aircraft radar systems in 1980, driven by the realization that Soviet aircraft were designed to survive nuclear environments where American fighters would be grounded. The hardening process involved shielding sensitive solid-state components with metal enclosures, adding surge protection circuits to prevent voltage spikes from reaching transistor junctions, and redesigning power distribution systems to isolate high-voltage transients. The modifications added 40 kilograms per radar system, increased production costs by 30%, and delayed the F-16 Fighting Falcon production schedule by 8 months while engineers integrated the hardening requirements into the existing design. The result was a radar that could survive EMP pulses at field strengths up to 20 kilovolts per meter, far below the 50 kilovolt threshold that vacuum tubes could withstand without hardening, but sufficient to provide some protection in a tactical nuclear scenario. The cost and complexity of retrofitting EMP hardening into solid-state systems highlighted the engineering advantage of vacuum tubes, which required no hardening because they were inherently immune to ionizing radiation, and it forced U.S. procurement offices to weigh the performance benefits of solid-state technology against the survivability benefits of older, simpler designs that Soviet engineers had never abandoned. Viktor Belenko received political asylum in the United States and began working as an aerospace consultant, providing detailed technical briefings on Soviet aircraft design, maintenance procedures, and operational doctrine. During one classified session with Air Force intelligence officers, Belenko confirmed that Soviet MiG-25 squadrons maintained aircraft availability rates exceeding 85%, a figure that had appeared in intercepted Soviet communications but had been dismissed by Western analysts as inflated for propaganda purposes. Belenko explained that the high availability was a direct result of the vacuum tube maintenance philosophy. Failures were frequent, but repairs were trivial, so aircraft spent less time grounded awaiting parts or depot-level maintenance. He described ground crews working in unheated tents at Arctic air bases, swapping tubes in -40-degree conditions, using portable generators and handheld test equipment, and he confirmed that the MiG-25 could be maintained by conscript technicians with 6 weeks of training, far less than the year-long training pipeline required for U.S. solid-state radar technicians. His testimony validated the engineering logic behind Soviet design choices and provided hard data that intelligence analysts used to revise their estimates of Warsaw Pact Air Force readiness, shifting the assessed balance of power in a way that influenced NATO force structure planning for the remainder of the Cold War. Soviet engineers never switched the MiG-25 fleet to solid-state radar technology, and vacuum tubes remained standard in the RP-25 system through the aircraft's retirement in 1991. The decision was deliberate and consistent with the aircraft's original design priorities. EMP resistance and high-power transmission were more important than weight reduction or miniaturization, and vacuum tubes delivered both without requiring the hardening, calibration, or logistics infrastructure that solid-state components would demand. Soviet doctrine assumed that any major air war would involve tactical nuclear weapons, and in that scenario, the ability to keep aircraft flying after EMP pulses had fried Western solid-state electronics was a decisive advantage. The MiG-25's designers had optimized for survivability in a nuclear environment, not for performance in a peacetime airshow, and the operational record vindicated that choice. Western engineers, working under different assumptions and constrained by different priorities, had built radars that were lighter, more efficient, and more precise, but also more fragile and more dependent on infrastructure that would not survive the first hours of a nuclear conflict. Neither approach was wrong, but the Soviet approach proved better suited to the scenario both sides actually prepared for, and the MiG-25's vacuum tubes became a case study in the difference between technological sophistication and operational effectiveness. The final assessment from the Foreign Technology Division, filed in 1981 and declassified decades later, concluded that Western solid-state technology provided significant advantages in precision, efficiency, and weight. But those advantages were undermined by vulnerability to EMP and susceptibility to high-power jamming in a nuclear battlefield scenario. Soviet vacuum tube radars, dismissed as primitive by Western analysts before the Belenko defection, could survive electromagnetic pulses that would destroy American solid-state systems instantly. And they could burn through jamming by transmitting power levels no Western aircraft could match. The report recommended a comprehensive review of U.S. electronic warfare doctrine, increased investment in EMP hardening for all tactical aircraft, and development of higher-power jamming systems. But it acknowledged that matching Soviet radar power in an airborne platform was not feasible given weight and thermal constraints. The conclusion was clear. In a conflict where nuclear weapons were used, Soviet brute force engineering would deliver operational capability, while American fighters sat grounded with fried electronics. And that capability gap represented a strategic vulnerability that procurement and doctrine changes could mitigate but not eliminate. The MiG-25's vacuum tubes had proven that sometimes the simplest solution was the most effective. And the lesson reshaped U.S. Air Force planning for a generation. The story of Viktor Belenko's defection and the MiG-25 radar teardown became a defining case study in the difference between technological sophistication and operational effectiveness. A lesson that influenced aerospace engineering and military procurement for decades. Western engineers had assumed that solid-state electronics represented unambiguous progress over vacuum tubes. But the MiG-25 demonstrated that engineering is always context-dependent. The best solution depends on the mission, the threat environment, and the logistical constraints, not on the novelty or complexity of the technology. Soviet engineers had chosen vacuum tubes, not because they lacked the capability to build solid-state systems, but because tubes met the operational requirements better in a nuclear war scenario, where EMP resistance, high power, and field maintainability were the metrics that mattered. The MiG-25 flew operational missions until 1991, and some of its design principles, particularly the prioritization of survivability over refinement, influenced Russian aerospace projects into the 21st century. Belenko lived the rest of his life in the United States, his defection a turning point in Cold War intelligence, and the aircraft he flew to Hakodate remained the fastest operational interceptor ever fielded, powered by engines that destroyed themselves at full throttle and guided by radar that could burn through jamming no Western system could counter. The vacuum tubes, mocked by engineers in 1976, had proven to be genius.